Hello learners, welcome you all to the lecture series on the course Functional Analysis, which is one of the core course of our MSc Mathematics program of IGNOU, MSc MACS. I am Professor Sujata Verma, Faculty of Mathematics, IGNOU, who is coordinating this course on functional analysis. We will start this lecture series by a talk by eminent mathematician Dr. Shravan Kumar, who is from IIT, Indian Institute of Technology, Delhi, and he will introduce you first to the norm linear spaces and some basic properties.
Hello learners, you know that this is a series of lectures on functional analysis. Today we are going to introduce the concept of norm linear spaces. Let us start. So, let me begin with the definition. Right. So, a norm linear space is a pair where X is a vector space over R or C, and the other one, this is a mapping from x to 0 to infinity, satisfying the following. First one, norm of x. So, this function what we have written, this is usually called as what is known as the norm, right. So, it should have the following properties, that it should always be, well, by definition it is greater than or equal to 0. So, I will say that this is equal to 0 if and only if x equal to 0. So, this is what is known as positive definiteness. Second one, norm of lambda x should be equal to mod lambda times norm x. So, this property is known as homogeneous or homogeneity, and the last one, what is known as norm of x plus y, because it is a vector space you can add two elements. So, norm of x plus y should be less than or equal to norm x plus norm y, and this should hold whatever we have written, this should hold for all x in x y from the vector space x and lambda from the scalar, right. So, we will write, so instead of writing it as R or C, we will write it as K. Well, so let me make a remark here at this stage. The remark is that, so throughout we are going to use only the space of complex numbers. So, throughout x will always denote a complex vector space, unless and otherwise mentioned, it is always going to be a complex vector space. So, unless and until we are using real vector space, will not mention whether it is complex or not, but it should be understood that it is a complex vector space, right. So, before we proceed further with examples and all those, let us look at some of the quick properties or quick remarks or quick observations. Maybe I will put it in the form of observations. First one is that if you have a normed linear space, then you define D, well I will define D from x cross x to 0 to infinity. How? It is defined as norm of x minus y. For those who have done a course on real analysis can easily observe that this is going to be a metric. So, this D is a metric on x, or equivalently the pair x comma D is a metric space. So, one may be wondering that what does this last one mean, that if you actually look into the properties of a metric, it has several, and the last one as we all know is what is known as the triangle inequality, and the triangle inequality here what we have here is exactly the triangle inequality that we wanted in the case of a metric, and therefore, this is also called as triangle inequality. So, once you have a metric, we can speak about, so one can speak about open sets or even open balls, and all notions related to a metric space. Right. You can even speak about convergence of a sequence, continuity, and all those things. Right. So, the first question is that do we have an example? Can we speak about some continuous functions? The answer is yes, and in fact, the second observation will give us a simple example. The second observation is that the mapping norm which we have from x to 0 to infinity. So, if you look at, so the first observation tells us that there is a metric here, and we know that there is already a metric on the 0 to infinity. So, with respect to these two metrics, this is a continuous map. The proof is not a difficult one. The proof runs as follows. So, before we go to the proof that this is a continuous map, let us first claim something else. The first claim is that norm satisfies the following claim, that is modulus of norm x minus norm y is less than or equal to norm x minus y for all x y in x. Right. So, how are we going to prove this? The proof is quite easy. So, let us fix first, let us fix let us in fact choose x and y from x, and then we are going to make use of the triangle inequality. Observe that norm x which is equal to norm x minus y plus y. Now, use the triangle inequality. If you use, this is going to be less than or equal to norm x minus y plus norm x norm y. So, let me bring this norm y to the other end. So, that will give us that norm x minus norm y is less than or equal to norm x minus y. So, if you notice this inequality, this is symmetric in x and y, because norm of x minus y is same as norm of y minus x. So, replacing or interchanging, the right term that I should use is interchanging. X and y. If you replace x by y and y by x, we will have norm y minus norm x. This is going to be less than or equal to norm x minus y. So, let me call the first one as 1 and the second one as 2. So, if you combine these two, so 1 and 2 together will imply that modulus of norm x minus norm y is less than or equal to norm x minus y. That is it. Right. Now let us go to the proof of the statement that we have made. Now, the proof should not be difficult, having done this much. So, how does one prove that a function is continuous? What we are going to do, our approach is something that is based on sequences. So, let x n be a sequence in X such that x n converges to X. Right. So, now we will have to show that norm x n converges to norm x. So, modulus of norm x n minus norm x, this is what we wanted. So, we will have to show that this goes to 0, right. So, if you use the above inequality, then this is less than or equal to norm x n minus x, right. So, let us start with an epsilon positive, let epsilon greater than 0. So, because x n converges to x, there exists n naught and n such that norm of x n minus x, this is going to be less than epsilon for all n bigger than or equal to n naught. Now, if I plug this into the above inequality, so this will imply that modulus of norm x n minus norm x, this is going to be less than epsilon for all n bigger than or equal to n naught. So, this is in fact equivalent to saying that norm x n converges to norm x. So, which in fact is equivalent to saying that the function norm is continuous, right. Maybe, so it has been a practice for me to use CTS for continuous. For those who are not familiar, I will write it as continuous, right. So, the main advantage here is the following, is that, so why do you need a vector space here? What is the role played by the vector space structure? In fact, that is given by the third observation. The role played by vector space structure and the matrix structure, because once you say that it is a vector space, then you will have what is known as the addition and scalar multiplication, while if you are in a matrix space setup where you can speak about convergence. So, the advantage here is that now that you have maps plus, which is addition from x cross x to x, the other one is the scalar multiplication, which is from C cross x to x. So, the whole point is that the first one is the addition, the second one is the scalar multiplication. These two maps are also continuous, wherein here we are going to take the product metric. Now, let us look at the first one. So, to show that these two are in fact, so these two maps, these two are continuous. So, in both these cases, x cross x as well as in C cross s x, in these two things we are going to use what is known as the product metric. right. So, let us look at let us choose two sequences, let x n and y n be any two sequences from x such that x n converges to x and y n converges to y. So, the claim is that the sequence x n plus y n converges to x plus y. Yes. So, how are we going to show this? So, let us begin with, so as usual let us begin with an epsilon positive, let epsilon greater than 0. Then so there exists n 1 in n such that norm of x n minus x, this is less than epsilon by 2 for all n bigger than or equal to n 1, and similarly we have y n converging to y, therefore, there exists n 2 in n such that norm of y n minus y, this is again less than epsilon by 2 for all n bigger than or equal to n 2. Now, we needed an n naught, so let us choose it as max of n 1 n 2. So, now we will have to show that x n plus y n converges to x plus y. So, let us subtract it from x plus y. So, we will have to estimate this difference. So, let us rearrange, this is x n minus x plus y n minus y, right. Now, we are going to make use of the triangle inequality. So, if you make use of the triangle inequality, this will be less than or equal to norm x n minus x plus norm y n minus y, and both are less than epsilon by 2, which is equal to epsilon, and we are done. That is exactly what we wanted here, right. The next one, well, having said all these things, these three observations, let us move on to some examples. Well, some of the familiar examples that we are already familiar with, we know the C, there is a natural norm, what is known as the modulus. So, this is this modulus is actually a norm on C. Well, the classical triangle inequality for the modulus, that is what we have generalized to a more general context of norm linear spaces. Now, let us do a more general example. You look at C n and we are going to define a norm. So, the space here is X C n, and then let us define a norm here. So, how are we going to do it? So, if I choose an x, it will be an n tuple x 1 x 2 up to x n, it is an n tuple here. So, let us define. So, I am putting a 1 here. Why this 1 will be clear soon once I define more examples. Let me define it as summation 1 to n mod x I. In fact, it will be a good exercise at this stage. So, I will leave it as an exercise that verify that this is a norm. This is one norm, whatever we have, this is a norm on C n. The next one. So, natural question is that do we have only one norm here? No, and there are in fact several norms. Let me choose same C x to be Cn. Now, let me define one more norm, which I am going to call it as the infinity norm, which is max 1 less than or equal to I less than or equal to n mod xi. Yet another exercise here is that again verify that this is a norm. Infinity is a norm, right. Right. So, let us move further, let us have some more examples. So, you should notice that it is still pending that why this 1 and infinity are here, which we will do it soon. Fourth one, this time let me introduce a new space L1. What is this? This L1 consists of all those complex sequences such that they are summable. Right. And now, let me define a norm here for a sequence. Let me define the norm on this space, which is nothing but summation over n in n mod x n. Right. Well, the same proof whatever we did here should tell us immediately that this is a norm. It is not a difficult one. So, I am leaving even this one as an exercise. Verify that this is a one is a norm on L1. So, natural question is why can't we do something like infinity? The answer is again yes, but not on L1. Here we will have a different space, what is known as L infinity. So, the elements of L infinity is all those complex sequences which are bounded, that means supremum over n in n mod x n, this should be finite, right. The same proof again whatever we did here in the case of infinity norm on C n, more or less the same proof, but you will have to be what should I say, you will have to be a bit alert because you are dealing with infinite case. There it's you will have only finite number of terms, here you will have infinite number of terms. So, you will have to be a bit alert. Yes. So, exercise here is that again, so well I need a norm here before I go to exercise. So, define a norm as supremum over n in n mod x n. So, then this is a norm on L1 L infinity, right. Right. So, now that we have 5 examples, right. So, I have to justify why this 1 and infinity in fact for well. So, let 1 less than p less than infinity. So, as usual we are going to look at, so I will introduce only, so I will do things fully for Cn and I leave it as an exercise to do it for Lp, because it is more or less the same proof, right. So, what we are going to do is that we are going to look at Cn, but with a different norm. So, it is an n tuple, p norm is summation 1 to n mod xi raised to the power p whole raised to the power 1 by p. This is the norm. So, the first thing that you will have to verify that it is a norm. So, in order to verify this, the most difficult one is what is known as the triangle inequality. So, in order to prove the triangle inequality, what we need is, so we will begin with an inequality, what is known as the Young's inequality, which is a fundamental inequality from calculus. Right. So, let x and y be non-negative real numbers and 1 less than p comma q less than infinity, such that 1 upon p plus 1 upon q is 1. Then the product x y is less than or equal to x raised to the power p upon p plus y raised to the power q upon q. Right. So, this is one of the fundamental inequalities which we will be using from calculus, right. So, now I think we are short of time. So, in the next lecture we will do what is known as Hölder's inequality and Minkowski's inequality, through which we will see that we are done with the triangle inequality, right, and then we will do more examples on infinite dimensional norm linear spaces, and we will also see more properties of the norm linear spaces. Thank you all.